Theory of Chapter 2, The Theory of Operation. The NVMe Express scalable interface is designed to address the need of the storage systems that utilize PCI Express-based solid-state drives or fabric-connected devices. The interface provides optimized command, submission, and completion paths. It includes support for a parallel operation by supporting up to 65,535 I/O queues with up to 64 KB minus one outstanding command per I/O queue. Additionally, support has been added up to has been added for many enterprise capability like end-to-end data protection, compatible with the SCSI protection information, commonly known as T10 DIF and SNIA DIX standards, enhance their reporting and virtualization. The interface has the following key attributes: does not require the uncacheable MMI register reads in the command submission or a completion path. A maximum of one MMI register will write or 164-byte message is necessary in the command submission path. Support for up to 65,535 I/O queues, with each I/O queue supporting up to 55,535 outstanding commands. Priority associated with each I/O queue with a well-defined arbitration mechanism. All information to complete 4 KB read request is included in the 64-byte command itself, ensuring efficient small I/O operation. Efficient and streamlined command set, supporting for MSIX, and interruption aggregation. Support for multiple namespaces. Efficient support for I/O virtualization architectures like SRIOV. Robust error reporting and management capabilities, and support for multipath I/O namespace sharing. This specification defines a streamlined set of the properties that are used to configure low-level controller attribute and obtain low-level controller status. These properties have a transport-specific mechanisms for defining access. For example, memory mapped items use registers, whereas the fabrics use the property get and the property set command. The following are examples of functionality defined in the properties. Indication of controller capabilities. Status for controller failure. Command status is provided via CQ directly. Admin queue configuration. I/O queue configuration is processed via admin command, and the doorbell registers for a scalable number of submission and completion queues. There are two defined constructions for communication between host and the NVMe subsystem: a memory-based transport model and a message-based transport model. All NVMe subsystems require the underlying NVMe transport to provide reliable NVMe command and data delivery. An NVMe transport is the abstract protocol layer independent of any physical interconnect properties physical interconnected properties. A taxonomy of NVMe transport, along with the examples, is shown in Figure 4. An NVMe transport may suppose a memory-based transport model or a message-based transport model. The message-based transport model has two subtypes: the message-only transport model and the message-memory transport model. A memory-based transport model is one in which commands, responses, and data transferred from between fabric nodes by performing explicitly memory read and write operations. A message-based transport model is one in which messages containing command captures and response captures are entered between the fabric node. The two subtypes of message-based transport models are differentiated by how data is sent by a fabric node. In the message-only transport model, data is only sent between fabric nodes using captures and messages. The message and memory-based airport model uses a combination of messages and explicit memory read and write operations to transfer command captures, response, captures, and data between fabric nodes. Data may optionally be included in command captures and response captures. Both message-only transport model and message model-based transport model are referenced as based models transport models throughout the specification when the description is applicable to both subtypes. An NVMe subsystem is made up of a single domain or multiple domains as described in section 3.2.4. An NVMe subsystem may optionally include a non-volatile storage medium and an interface between the controller of the NVMe subsystem and the non-volatile storage medium. Controllers expose this non-volatile storage medium to a host throughout namespaces. An NVMe subsystem is not required to have the same namespace attached to our controller. An NVMe subsystem that supports a discovery controller does not support any other controller type. A discovery service is an NVMe subsystem that supports discovery controller only. Refer to section 3.1. Figure 4. Taxonomy of transport models. The capability and settings that are applied to an NVMe Express controller are indicated in the Controller Capabilities (CAP) property and the Identified Controller Data Structure, referred to Figure 275. A namespace is a formatted quantity of the non-volatile memory that be accessed by a host. Associated with each namespace is an I/O command set that operates on that name message. Mhm. An NVMe Express controller may support multiple multispaces as referenced using a namespace ID. Namespaces may be created and deleted using the namespace management and capacity management command. The identify namespace's data structure. The IO command set specific identify namespace data structure. And the IO command set the independent identify namespace data structure indicate capabilities and settings that are specific to our particular namespace. The NVMe Express interface is based on a paired submission and completion queue mechanism. Commands are placed by software into a submission queue. Completions are placed into associated with the completion queue by the controller. There are three types of command that are defined in the NVMe Express: admin command, an IO command, and a fabric command, and feed command. Figure 5 shows these different command types. Figure 5 types of NVMe command sets. An admin submission queue and associated completion queue exist for the purpose of controller management and control. For example, creation and deletion of IO submission and completion queues, a working command, and etc. Only commands that are part of the admin command set or the fabric command set may be submitted to the admin submission queue. An IO command set is used with an IO pair queue. This specification defines common IO command queue commands. This specification defines a common IO command. IO command sets are defined in NVMe IO command set specification. For example, NVMe command set, key value command set, or joint namespaces command set. The fabric command set is NVMe over fabric specific. Fabric command set commands are used for operations specific to an NVMe over fabrics, including establishing a connection. The NVMe in-band authentication and getter or a setup property or fabric commands may be submitted to the admin submission queue, and some fabric command may also be submitted on the IO submission queue. Unlike admin or IO command, fabric commands are processed by a controller regardless of whether the controller is enabled. That is, regardless of the state of cc.en. 2.1. Memory-based transport model. In the memory-based model, submission and completion queues are located in memory. Software creates queues up to maximum supported by controller. Typically, the number of command queues created is based on the system configuration and unexpected workload. For example, on the 4-core processor-based system, there may be queue pair per core to avoid locking and ensuring data structures are created in the appropriate processor core's cache. Figure 6 provides a graphical representation of the queue pair mechanism, showing a 1 versus 1 one-to-one mapping between submission queues and completion queues. Figure 7 shows an example where the multiple I/O submission queues utilize the same I/O completion queue on core B. Figure 6 and Figure 7 shows that there is always one-to-one mapping between the admin submission queue and admin completion queue. Okay, Figure 6 is queue pair example, one-to-one mapping. And Figure 7 is queue pair example and to one mapping. So submission queue (SQ) is a circular buffer with a fixed slot size that a host software uses to submit the command for execution by the controller. The host software updates in the appropriate SQ tail doorbell register when there one to n new command to execute. The previous tail value is overwritten in the controller when there is a new doorbell register write. The controller fetches SQ entries in order from the submission queue and may execute those commands in any order. Each submission queue entry is a command. Commands are 64 bytes in size. The physical memory location in memory to use for data transfers are specified using physical region page (PRP) entries or scatter gather list (SGL). Each command may include 2 PRP entries or one SGL segment. If more than 2 PRP entries are necessary to describe the data buffer, then a pointer to a PRP list that describes a list of PRP entries is provided. If more than one SGL segment is necessary to describe data buffer, then the SGL segment provides a pointer to the next SGL segment. A completion queue (CQ) is a circular buffer with a fixed slot size used to post status for completed command. A completed command is uniquely identified by a combination of associated SQ identifier and command identifier that is aligned by host software. In the memory-based transport model, multiple submission queues may be associated with a single completion queue. This feature may be used where a single worker thread processes or this feature may be used where a single worker thread processes or commands completion via the completion queue, even when those commands originated from multiple submission queues. The CQ header point is updated by host software. Header point is updated by the host software after processing completion queue entries indicating the last free CQ slot. A phase tag P bit is defined in the completion queue entry to indicate where an entry has been newly posted without consulting a register. This enables host software to determine whether a new entry was posted as part of the previous or current round of completion notifications. Specifically, each round through a completion queue entries, the controller inverts the phase tag bit. 2.2 Message-based transport model. Okay. The message-based transport model used for NVMe over Fabrics has the following differences from the memory-based transport model. If there is a one-to-one mapping between I/O submission queues and I/O completion queues. NVMe over Fabric does not support multi-I/O submission queues being mapped to a single I/O completion queue. NVMe over Fabric does not define the interrupt mechanism that allows the controller to generate a host interrupt. It is the responsibility of the host fabric interface, for example, host bus adapter, to generate host interrupt. The NVMe over Fabric uses a different mechanism for I/O submission queue and I/O completion queue creation and deletion. NVMe over Fabric does not support transferring metadata from a separate buffer. For example, does not support the meta pointer field referred to Figure 87. NVMe over Fabric does not support PRPs but requires the use of SGRs for admin, IO, and Fabric commands. This differs from the memory-based transport model where SGRs are not supported for admin commands and optional for IO commands. The NVMe over Fabric does not support completion queue flow control. This requires that the host ensure there are available completion queue slots before a submission queue new command, and NVMe over Fabric allows submission queue flow control to be disabled if the controller and controller agree to disable it. If the submission queue flow control is disabled, the host is required to ensure that there are available submission queue slots before submitting new commands. 2.2.1 Fabric and Transport. NVMe over Fabric utilizes the protocol layer shown in Figure 8. This specification defines core aspects of the architecture that are independent of NVMe transport. An NVMe transport binding specification is used to describe any NVMe transport specification specific specialization as well as the how service required by the NVMe interface are mapped to on corresponding NVMe transport. The native Fabric communication services and other functionality used by the NVMe interface and NVMe transport. For example, the Fabric protocol and the Fabric physical layers in the Figure 8 are outside the scope of the NVMe family of the specification. NVMe Figure 8 NVMe over Fabric layering. 2.2.2.2 NVMe subsystem ports. An NVMe subsystem presents a collection of 1 to 64 KB minus 16 controllers which are used to access the namespaces. The controller may be associated with a host through 1 to 64 KB NVMe KB NVM subsystem port. Is it KB, right? Yes. An NVM subsystem port is a protocol interface between the NVM subsystem and the Fabric. An NVM subsystem port is a collection of one or more physical Fabric interfaces and interfaces that together act as a single protocol interface. When link aggregation, for example Ethernet, is used, the physical ports of a group of aggregated links constitute a single NVMe subsystem port. An NVMe subsystem contains one or more NVM subsystem ports. Each NVMe subsystem port has a 16-bit port identifier, port ID. An NVMe subsystem port is identified by the NVMe subsystem NVMe qualified name (NQN) and the port ID. The NVM subsystem port of an NVM subsystem may support different NVMe transport. An NVM subsystem port may support multiple NVMe transport if more than one NVMe transport binding specifications existing for the underlying fabric. For example, an NVMe subsystem port identified by a port ID may support both IWRP or ROCE. ROCE. The NVMe subsystem implementation may bind the specific controller to a specific NVMe subsystem port or allow the flexible allocation of a controller between NVMe subsystem port. However, once connected, each specific controller is bound to a single NVMe subsystem port. A controller is associated with exactly one host at a time. NVMe over Fabric allows multiple hosts to connect to a different controller in an NVMe subsystem through a same NVMe subsystem port. Or other aspect of the NVMe over Fabric, multi-path I/O and namespace sharing, referred to section 2.4.1, are equivalent to that of a memory-based transport model. 2.2.3 Discovery Service. NVMe over Fabric defines a discovery mechanism that a host uses to determine the NVMe subsystems that expose namespaces that the host may access. The discovery service provides a host with the following capabilities: the ability to discover a list of NVM subsystems with the namespaces that are accessible to the host. The ability to discover multiple paths to an NVM subsystem. The ability to discover the controller that are statically configured. The operational ability to establish explicit persistence connections to the discovery controller, and the optional ability to receive asynchronous event notifications from the discovery controller. A discovery service is an ambient subsystem that supports the OmniDiscover controller, referred to section 3.1.2.3, and it shall not support any other controller type. The method that a host uses to obtain the information necessary to connect the initial discovery service to implementation specific. This information may be determined using a host configuration file, a hypervisor, or OS properties, or some other mechanism. 2.2.4 Captures and Data Transfer. A capture is an NVMe unit of information exchange used in NVMe over Fabric. A capture may be classified as command capture or a response capture. A command capture contains a command formatted as a submission queue entry and may optionally include SGLs or data. A response capture contains a response formatted as a completion queue entry and may optionally include data. Data transfers to any data transferred at an NVMe layer between a host and an NVM subsystem. For example, a logical block data or a data structure associated with a command. A capture is independent of any underlying NVMe transport unit. For example, packet, message, or a frame and associated headers or footers, and may consist of multiple such units. Command captures are transferred from a host to an NVMe system. The SQE contains an admin command, an IO command, or a fabric command. The minimum size of a command capture is NVMe transport binding specific, but shall be at least 64 byte in size. The maximum size of a command capture is NVMe transport binding specific. The format of a command capture is shown in Figure 9. Figure 9 Command Capture Format. Responses captures are transferred from an NVMe subsystem to a host. The CQE is associated with the previously issued two admin command, IO command, and fabric command. The size of a response capture is NVMe transport binding specific, but shall be at least 16 byte in size. The maximum size of a response capture is NVMe transport binding specific. The format of the response capture is shown in Figure 10. Figure 10 response capture format. The NVMe transport using a message-only transport model and message model transport that requires all SGL sent from the host to controller be transferred with the command. They may optionally support the transfer of a portion or data within the command and response captures. NVMe over Fabric requires SGL for a command, Fabric, admin, and I/O. An SGL may specify the placement of data within a capture or the information required to transfer data using an NVMe transport-specific data transfer mechanism. For example, by memory transfers as in RDMA. Each NVMe transport binding specification defines the SGLs used by a particular NVMe transport and capture SGL and data placement restrictions. 2.2.5 Authentication. The NVMe over Fabric supports both Fabric secure channel that includes authentication, referred to section 8.13.1, and NVMe in-band authentication. The An NVM system may require a host to a Fabric secure channel, an NVMe in-band authentication, or both. The discovery service indicates if the Fabric secure channel shall be used for an NVMe subsystem. The connector response indicates if the NVMe in-band authentication shall be used with that controller. A controller associated with the NVM subsystem that requires a Fabric secure channel shall not accept any command. For example, Fabric command, admin command, or IO commands on an NVM transport until a secure channel is established. Following a connected command, a controller that requires NVMe in-band authentication shall not accept any command on the queue created by the connect command or the authentication command until NVMe in-band authentication has completed. Refer to section A.13. 2.3 NVM storage model. 2.3.1 Storage entities. The NVM storage model includes the following entities: NVM subsystems, refer to 1.5.40, domains, refer to section 3.2.4, endurance groups, refer to section 3.2.3, NVM set, refer to section 3.2.2, NVM spaces, refer to section 3.2.1. As illustrated below, each domain is contained in a single NVMe subsystem. Each endurance group is contained in a single domain. Each NVMe set is contained in a single endurance group, and each namespace is contained in a single NVMe set. Each media unit is contained in a single endurance group. Each endurance group is composed of a storage media, which terms media units refer to section 8.3.2. For clarity, media units are not shown in the example that follow. Figure 11 shows the hierarchical relationship of these entities within a simple NVMe subsystem, which has one domain and one endurance group and one NVM set and one namespaces. Figure 12 shows the relationship of these entities in the complex NVMe subsystem, which has multiple domains, multiple endurance groups per domain, multiple NVM sets per endurance group, and multiple namespaces per NVM set. Figure 12. Complex NVM storage hierarchy. Entity naming key ABC. A. Domain, capital letter. B. Endurance group, digit. And C. NVM set, lowercase letter. Digit. Reporting on endurance groups or NVM sets is optional, but the storage model supports these concepts. An NVM subsystem may be shipped by the vendor with its storage entities configured. or it may be configured or reconfigured by the customer. Typical changes to the configuration are creation and deletion of namespaces. Mhm. On NVM subset that does not support multiple NVM sets does not require reporting over NVM sets. An NVM subsystem that does not support multiple endurance groups does not require reporting of endurance groups. 2.3.2 IO command sets. IO command IO command perform operations on namespaces, and each namespace is associated with exactly one IO command set. For example, commands in the command NVM command set access data represented in a namespaces as logical blocks, and commands in the key value command set access data represented in a namespaces as key value pairs. The association of a namespaces to an IO command set is specified when the namespace is created and is fixed for lifetime of the namespace. A controller may support one or more IO command sets and may be attached to the namespaces associated with different IO command sets. A host issues command to a namespace, and those commands are interpreted based on the IO command set associated with that namespace. 3.3 NVM subsystem examples. Figure 413 illustrated a simple NVM subsystem that has a single instance of each storage entity. Figure 13 single namespaces NVM subsystem. The subsystem consists of a single port and a single domain. The domain contains the controller and storage media. All of the storage media are contained in one endurance group. All of the storage media in that endurance group are organized into one NVM set. The NVM set contains a single namespace. Figure 14 shows a NVM subsystem with two namespaces. Figure 14, two namespace NVM subsystem. An NVM subsystem may have multiple domains, multiple namespaces, multiple controllers, and multiple ports as shown in Figure 15. Figure 15, complex NVM subsystem. Number 2.4, extended capability theory. 2.4.1, multipath I/O and namespace sharing. This section provides an overview of a multipath I/O and namespace sharing. Multipath I/O refer to two or more completed independent paths between a single host and namespace, while namespace sharing refer to the ability for two or more hosts to access a common shared namespace using different NVM Express controller. Both multi-path I/O and the namespace sharing are multi-path I/O and the namespace sharing require that the NVMe subsystem contain two or more controllers. The NVM subsystems that support multi-path I/O and namespace sharing may also support asymmetric controller behavior referred to the section 2.4.2. Concurrent access to a sharing namespace by two or more hosts requires some form of the coordination between hosts. The procedure used to coordinate these hosts is outside the scope of this specification. Figure 16 shows an NVMe subsystem that contains contains a single NVMe Express controller implemented over PCI Express and a single PCI Express port. Since this is a single function PCI Express device, the NVM Express controller shall be associated with the PCI function 0. A controller may support multi namespaces. The controller in Figure 16 supports two namespaces labeled NSA and NSB. Associated with each controller namespace is a namespace ID labeled as NSID1 and NSID2 that is used by the controller to reference a specific namespace. The namespace ID is distinct from the namespace itself and is the handle a host and the controller use to specify a particular namespace in a command. The selection of a controller namespace IDs is outside the scope of this specification. In this example, namespace ID 1 is associated with the namespace A, and namespace ID 2 is associated with the namespace B. Both namespaces are private to the controller, and this configuration supports neither multipath I/O nor namespace sharing. The figure 16 namespace NVMe Express controller with two namespaces. The figure 17 shows a multi-function NVMe subsystem with a single PCI Express port containing two controllers implementing NVMe over PCIe. One controller is associated with the PCI function 0 and the other controller is associated with the PCI function 1. Each controller supports a single private namespace and access to sharing namespace B. The namespace ID shall be the same or controllers that have access to a particular shared namespace. In this example, both controllers use namespace ID 2 to access shared namespace B. There is one or more identified controller data structure for each controller and one or more identified namespace data structure for each namespace referred to figure 273. Controllers with access to a shared namespace return the identified namespace data structure associated with the shared namespace. That is, the same data structure contents are returned by all controllers with access to the same shared namespace. There is a globally unique identifier associated with the namespace itself, and it may be used to determine whether there are multiple paths to the same shared namespace. Refer to section 4.5.1. Controllers associated with the shared namespace will operate on the namespace concurrently. Operations performed by the individual controllers are atomic to a shared namespace at the right atomicity level of the controller to which command was submitted. Refer to section 3.4.3. The right atomicity level is now required to be the same across controllers, the shared namespace. If there are any ordering requirements between the command issued to different controllers that access a shared namespace, the host software or an associated application is required to enforce these ordering requirements. Figure 18 illustrates an NVM subsystem with two PCI Express ports, each with the associated with controller implementing NVMe over PCIe. Both controllers map to PCI function 0 of a corresponding port. Each PCIe Express port in this example is completely independent and has its own PCIe Express fundamental reset and reference clock input. A reset of a port only affect the controller associated with that port and has no impact on the other controller. Shared namespace or operations performed by the other controller on shared namespace. The functional behavior of this example is otherwise the same as that illustrated in Figure 17. The Figure 18 NVMe sustain with two controllers and two ports. Yeah, the two ports or shown in figure 18 may be associated with the same root complex or different root complexes may be used to implement both multiple I/O and I/O sharing architectures. System-level architectural aspects and the use of multiple ports in a PCI Express fabric are beyond the scope of this specification. Figure 19 illustrate an NVM subsystem that supports single-root I/O virtualization (SRIOV) and has one physical function and four virtual functions. An NVMe Express controller implementing NVMe over PCIe associated with each function, with each controller having a private namespace and access to a namespace shared by all controllers, labeled NSF. The behavior of controllers in this example parallels that of the other examples in the section. Refer to section 8.26.4 for more information on SRIOV. The figure 19 PCI Express device supporting single root I/O virtualization. And the examples provided in this section are meant to illustrate concepts and not are not intended to enumerate all possible configurations. For example, an NVM subsystem may contain multiple PCI Express ports, with each port supporting SRIOV. 2.4.2 Asymmetric controller behavior. Asymmetric controller behavior occurs in NVMe subsystem where no system space access characteristics namespace access characteristics, for example performance, may vary based on the internal configuration of an NVM subsystem or which controller is used to access a namespace, for example fabric. The NVM subsystem that provide asymmetric controller behavior may support asymmetric namespace access reporting as described in section 8.1. Okay, today I think the section chapter 2 is over.